你还是，不过你今天3点还是正常去，没有多少人工作是吧？哦，今天是。
Oh, we said together whenever we want to Zoom, just shoot off for 20 minutes. Or 2 hours. I just don't like you stuff. Yeah, I know. Yes, it is. Outside factors.
Did anyone get their displays working or try that? Get that working? Yeah. So I sent out email, I think, to everyone with, there were just some bugs in the original software that what I want to do is actually, so things are a little screwy here with the end of the semester and essentially finals online. I'm not doing finals online, but then by the same token, I don't want to give 3 exams on the same day to the students I have in EMAG 310 and 354. So what I'm proposing is actually have this exam a week from Friday. So, and then we'll still have Monday and Wednesday the following week. We won't have class after the exam this next Friday, but the last project, which I'll assign today, will then be due on the Tuesday before the final Wednesday. So does that sound reasonable, agreeable? So we will actually lecture Friday and Monday, cover some more topics, but then we'll review on Wednesday for our last exam on a week from Friday. So we'll do that. And then I'll give you your last, try to get your last project posted today. I think everyone's ready for the semester to be over. Things be better this spring. Okay, I want to finish up. We're still in chapter 8. So some of the material today will actually be related to the last project that I want to assign. But there are a couple of other so we started looking at binary actuators and interfacing binary actuators. In most cases, we're just using still the general purpose I/O pens. So this is binary actuators continued. When I get started earlier, I thought my alarm went off. So I want to look at actually DC motors today, and then we'll look at a special technique called pulse width modulation that you can use for motor speed control. So we've already looked at transistor interfaces, interfacing relays, turn things on and off, higher voltages, higher currents with a microcontroller. We looked at solenoids, all relatively simple interfaces that, binary actuators means you're going to interface to GPIO. Okay. So let's look at a DC motor, and I'll show you a particular circuit. It's called an H-bridge circuit. That can be used to run a motor in either forward or reverse. And there's all kinds of different motors. There's DC motors, AC motors. There are stepper motors as well. This is just what's called a small DC motor. And so I'm not going to show the microcontroller interface yet, but we're going to use 4 switches, and then we'll talk about how to use the switches for motor control. And then so DC motor is pretty simple. Put a DC voltage across it at the right voltage. So this is an M to represent the motor. And let me label the switches: S1, S2, S3, S4. If we hook the motor up right across the supply, the motor would turn. If we switch the polarity on the terminals, the motor would turn in the opposite direction. So the idea with this H-bridge circuit is that, if we closed S1 and S4, then we've got a path this way through the motor, leaving S2 and S3 open. Closing S1 and S4, we've got a path this way. Then, we could, if we wanted to run the motor in reverse, we would close S3 and S2 while opening up S1 and S4. So with 1 and 4 closed, I'm going to call that the forward direction. And with how you spell reverse? With 2 and 3 closed, it would run in the opposite direction. With all 4 open, it's in what's called a coasting mode. Okay, so it'd be a way to slow down the motor. If you actually short, you could do this with shorting S2 and S4, for example. Notice with S1 and S3 open, you wouldn't be shorting the supply, but if you short S2 and S4, or S1 and S3, there's still no current path. That's when you short the terminals on a DC motor, it acts like a brake. So that would be a fast stop mode. So you can get those 4 different types of behavior from this H-bridge circuit. Now, what we want to do is actually control these switches with a microcontroller. So the switches, they could be relays, they could be bipolar junction transistors or MOSFET transistors, all connected to MOSFETs. But typically, you can get an H-bridge on an IC. Okay, and that's the easiest way to go, especially for its design to actually be connected to a microcontroller. I'm going to show you a particular IC. The L293 from Texas Instruments contains 4 what are called half H drivers. You can use a half H driver if you want to just run the motor in one direction. Okay, but if you use 2 half H drivers, you get a full H, which is what we need. But this has 4 half H's, so you actually have 2 full H bridges on this thing. So here's the connections for the 293. Got 4 pins here. I think it's actually a 16-pin device. This is 1, 7, 2, 16. You can look this up and find actually the application section on the data sheet for this particular IC, and it'll show you how to hook it up for if you want to run a motor in one direction or another direction, how to use it in the half H mode. And I'll show this diagram for the full H mode. Pins 2 and 7 here. These are inputs to 2 of these switches, actually, and then these are connected to our microcontroller. I'm just going to call them out 1 and out 2. But this little IC is designed to directly interface to microcontroller output. And then this 5-volt level provides the level for all the logic circuit. And let's see, there's 4 pins here on the output. 4, 6, 3, and 8. Actually, 4 and 5 are both grounded. And our motor gets connected between pins 3 and 6. And this is our motor supply voltage. So it might be, 12-volt motor. So this is a separate supply voltage than our logic supply voltage. Now we also need all the Snubber diodes here. So there's actually a pair here. Because the motor has inductance. So these are necessary. I'll show it up here. These are necessary so that you don't get the large back voltage, back EMF when you try to shut the motor off and destroy the chip. And then there's another pair here. And normal operation, those diodes aren't conducting current until you shut the motor down. This is the L293H driver. And you'll find this table in the data sheet. To get it to go forward, output 1 has to be high and output 2 has to be low. To get it to run in the opposite direction, these are reversed. Okay, so it's not just controlled by 1 pin. You have to take 1 pin high while you take the other one low. And then if they're both low, actually, or both high, it's in a braking mode. This particular configuration doesn't allow for a coasting mode where it's disconnected. Now, if you hook up, let's get another marker. If you hook up the DC motor across the, whatever the rated supply voltage is, across 12 volts, it'll run at full speed. So pulse width modulation, usually abbreviated PWM, allows us to actually control the speed of the motor, or actually control like the brightness of an LED. Instead of having it on or off all the time, we switch it on and off at a fast enough rate. So the idea is signal might look like, might be high for a very long time and then low briefly. Now, typically when you're doing PWM control, you keep the period the same, but then vary the high time within the period. So this would be, you know, full power. You keep it on all the time. I put a little low there, but that would essentially be full power or high power mode. If it were just high half the period, now this is a periodic waveform, so this would, you know, repeat. So this would be like half speed for your motor, or half brightness for your LED. And then the last one would be, you know, high for just a really brief period of time, and then low. And that would be like a low power or a slow speed for a motor. But that's the idea, that you would actually just toggle this pin. And you have to be careful, not all devices can be controlled like this, but a DC motor can be. Brightness to most incandescent bulbs and LEDs can be controlled this way as well. And PWM can be implemented using just the delay routines that we've already used. Now I'll mention that most microcontrollers that have timers that you can connect to outputs that can directly generate the PWM waveform that you need. And then you just vary the parameters of the timer to adjust the duty cycle of the waveform is the high time over the period, the high plus low time. So this top one here would have almost 100% duty cycle. This would be a 50% duty cycle when that high time is equal to the low time. And this is maybe more like a 10% duty cycle waveform. But most microcontrollers have a timer. You just write values to control registers and it'll automatically generate the PWM waveform for you. And then you can change those parameters to change the duty cycle. And our microcontroller will do that through the timer A. I'm not going to get into the details of that. We're going to look at a simpler implementation, just using initial high time in milliseconds. You would have to play around with, and this is what you have to do on your project, is actually play around with what period you want. Because with our implementation, you could do this over a second, but we're going to be set up so that, after a period, you're going to examine the switches. So you'll get more responsiveness, be able to read the switches at a greater rate if you use a smaller period. So here, we'll say you're setting up an initial high time and initial period. Obviously, for an LED control, you wouldn't want this to be so long that you would actually notice the LED flash on and off, right? But if you do that fast enough, your eye can't really detect changes, that are faster than maybe 30 times a second. You turn it off and on and off at a faster rate than that, you can actually see it go on and off. But your eye actually has some latency. If you make it too slow, though, you get the annoying flicker. Certainly, if you start turning it on and off at something like 10 times a second, you'll probably notice flicker in that case. So you have to play around with the period, the rate at which you want to turn it on and off. But then in our while loop, this would, of course, we've been using this most of the semester now. That would set that corresponding output high. And then we would delay. That's not the exact name of the delay routine that we've been using, but you get the idea. That would delay then for 100 milliseconds with that high. And then we could set it low. This is the notation we've been using. So turn that bit off, leaving the other outputs unchanged. And then here, our delay in milliseconds would be T minus high would be our load time. Then now continuing this, we obviously have to examine some input. It might be an input from a potentiometer, reading a voltage level. Here I'm just going to say we're examining two switches. If one switch is pressed, we're going to increase the duty cycle. If the other switch is pressed, we're going to decrease it. So something like this, if switch one is low, and H is less than 200, we'll increase the high time. Else, if the other switch is low and H is greater than 0, we'll decrease the high time. So this would be a very simple program that would allow you to vary the duty cycle, to a DC motor, vary it between, full control, duty cycle of 100% to complete turning it off. Okay. With something like an LED, you should see the LED brightness vary from off to, maximum brightness. Okay. So any questions about that? Okay, what I wanted to do today is actually, did everyone get the software for the LCDs running and know how to get that set up on their board? Do I need to go through that again? And your last project will have you using the LCD display to write information to the display. So in that, you've got that example program. In that example program, that they show how to write a bitmap output, write an image out to the display. I'm not going to have you do that. I'm just going to have you do ASCII output for your final project. But it shows you in the test program, it shows you how to write out a string, how to write out a character, how to move the cursor to a particular position on the display. You know, I think all those routines are fairly straightforward. You have to initialize, call the initialize routine first. But I think all the available routines in that Nokia 5110.c program, just look through that for what you need. There's a routine in there that actually you can use to convert a number into a character string. I really don't know why he has that, because you can use sprintf to convert any number to a string and then feed it to the string output routine, which is the way I would do it. He's got this specialized routine that only works for unsigned 16-bit numbers, but again, you could use sprintf to do that conversion easily, or do that conversion outside of without using the library routine. Okay. So I'll give you the rest of the period to work on. I can try and help you with get your displays wired up. Our boards are wired a little differently than the board he has in the book. If you want to use the backlight, I don't suggest it. You don't need it, but you have to connect the backlight to ground, whereas in the figure in the book, he has the backlight going to the 3.3 volt display, but it just lights up 4 LEDs. Those LEDs tend to use a lot of current, so you can limit the amount of current by using a 100 ohm resistor. Again, you can see the display fine in daylight without using the backlight, so there's no need to actually make that connection. All right, so I'll be around to help you if you have wiring issues. I think otherwise the wiring diagram is just like the one in the book, right? Just don't connect the backlight to anything. And then the programs I had on the website then, under the Lecture 31 area, download those, build that project, make sure you can see something on your display.